alternating voltage or current, alternating signals we represent, for example, voltage, which is function of time, we can call instantaneous voltage. It is equal to V0 sine omega t. This is a basic way in which the alternating, particularly sinusoidal voltage, can be represented. Here V0 is amplitude of the signal, omega is the angular frequency, which we can write omega equal to 2 pi f, and it can also be written as 2 pi over t, where capital T represents time period of the signal. Now the dimensions of omega, they are reciprocals of time, so we can write m0 L0 t minus 1, and omega t will be a dimensionless quantity. So here, that is the angular part. One can think of theta there if it is a static kind of situation, and theta is equal to omega t when omega is the angular frequency and the time is continuously flowing time. In Indian conditions, we have frequency 50 Hertz, that is 50 cycles per second. V0, amplitude of the signal is 220 to 40 volts. So omega, which is equal to 2 pi f, we can write 314.16 radians per second, and time period, which is a reciprocal of frequency 1 by 50, we can have 0.02 seconds. It means that one complete cycle is described in the time 0.02 seconds. Now, here we can have a graphical representation of what we are talking about. So here voltage is rolling over from 0 volts to 220 volts, then back to 0 volts, then minus 220 volts, and then again back to 0 volts. This whole stuff is taking its course in 0.02 seconds. In other words, one can say such a 50 cycles will be established in 1 second. Here we have a small animation of how circular motion is related to sinusoidal signal generation. So theta, which is omega t, you can say, is describing over a complete cycle, and as the theta rolls from 0 to 2 pi, the sinusoidal signal, which is sine theta or sine omega t, that is described in this fashion. Now, if one likes to talk in terms of current, current will be obviously derived by the load circuit or load resistance or any application device, and it depends on the resistance offered by the device or circuit, and it can be represented by I0 sine omega t, where I0 is amplitude of the current, and omega I have replaced 2 pi over t. So 2 pi over t into t, so these dimensions are cancelled. I mean, it is a dimensionless quantity, and over one complete cycle, that is small t, when it rolls from 0 to capital T, so in that, if you replace small t by capital T, it is sine of 2 pi. So this is how one complete cycle is represented. Here, if I consider current to be unity, I mean amplitude of the current is say 1 ampere, then I of t, that is instantaneous value of current, can be represented by omega, that is 314.16 into t, omega t. So same graph in blue color is reserved for now current, and red color is reserved for voltage representation. And sometime when we like to see both the quantities together, maybe the scale is different for current and voltage, but the colors will let us identify how the things are moving. Now, average current. Average current is the net current delivered in one complete cycle. So in the positive half cycle, current is going clockwise in the circuit, and in the negative half cycle, current is going in the reverse direction. Both the contours above x-axis or above time axis and below time axis, they are symmetric and opposite, and one can easily conclude that the average of such a contour, sinusoidal one complete cycle, will be zero, and obviously the average current in the circuit in one complete sinusoidal cycle is zero. Now, even though this average current is becoming zero, it doesn't mean that the power is not delivered in the circuit. Power is delivered during positive half cycle as well in the negative half cycle. Now let us go mathematically. I average we shall define as a ratio of two integrations. The integration in the numerator is I of t dt, that is instantaneous value of current is integrated, or rather summed over dt in one complete cycle, that is small t is rolling from 0 to the time period of the signal, divided by the total time period of the signal, that is capital T. So integration dt is t, and upper limit minus lower limit will yield capital T. Now integration 0 to capital T, I0 sine omega t is 0, and obviously the average current is 0. Now the beginner may face a difficulty in understanding how this integration in the numerator is becoming 0. So I would like to quickly explain that as integration of sine omega t is cos omega t upon omega with a minus sign, and it is rolling from 0 to capital T. So upper limit minus lower limit I0 upon omega you can take out, or even you can take out the minus sign, and here we are left with cos of 2 pi minus cos of 0, or rather minus cos of 2 pi minus cos of 0. So here as the cosine function is periodic having same value at 0 and 2 pi, this integration vanishes. So it would be better, people thought it would be better to define the average current over a half cycle. This is one very important concept, and if we do so, the integration in the numerator will not be 0, and this time this integration sine omega t dt will be t upon 2 pi, capital T upon 2 pi. The cycle we are considering is in terms of time, which is in the denominator. It is again t upon 2 pi. So we end up with the final value twice I0 upon 2 pi. So 0.637 times I0. I0 is the amplitude. So 63.7% of I0 will be the average current delivered in the half cycle. So here, if someone likes to get into this integration, sine omega t dt over the limits 0 to t by 2, capital T by 2, then you can understand that this integration is again minus cos of omega t upon omega over these new limits 0 to capital T by 2, and this time it is I0 capital T upon pi. This time it is not 0. Now root mean square value. Here we are having IRMS value, I square RMS into R into capital T. So here we are doing calculation for one complete cycle. So I square R is the power delivered. So IRMS we are going to define from this, This is equal to the instantaneous value of current square. This current is function of time. That current square into R dt or one complete cycle. So here we have integration. You can take I0 out of the integration sign, and we are left with integration sine square omega t, which rolls over 0 to capital T. Now, this is a sine square integration. You need a trigonometric substitution. Sine square theta is equal to 1 minus cos 2 theta upon 2. So the square is eased out and the integration becomes simple. Now, the left hand side I RMS square RT is equal to 1 by 2 R I0 square into this green bracketed equation. This is with a value capital T. Later on I'll tell you how that integration can be solved. So I square RMS after simplification becomes I0 square upon 2. So I RMS is equal to I0 upon root 2. In the same fashion, you can again write the equation for VRMS, which is equal to V0 upon root 2. So let us quickly go through the integration. So integration, the first part is 1 and second part is minus cos of 2 omega t. So first part integration will be t, where limits roll from 0 to capital T, and in the second part we have integration cos of 2 omega t as sine of 2 omega t upon omega, where the limits again go from 0 to capital T. So this integration, second part, also amounts to 0, and the net result is capital T. So here this capital T value we have substituted in this integration. Now the average current is 0 in one complete cycle. Here the green line indicates the sinusoidal current in the circuit, and on the x-axis, instead of showing time, I have shown angle, because this is basically angle omega t. Now this angle is subdivided into the routine intervals that we normally encounter, and now we shall see how the current in the circuit rolls. So I average current. So in the positive part something is being delivered, and in the negative half cycle that is withdrawn, so the net result is 0. So here the blue line which is falling on x-axis, time axis or theta axis, it is shrinking to the 0 value. So average current delivered is 0. I average in half cycle is, we have just seen, it is 0.637. So if you take amplitude unit, so at 0.637 you have average value for half cycle. And then we have discussed IRMS for complete cycle, and it is 1 upon root 2 times I0. As I0 is unity, it is 0.707 of the maximum value. So this is the I average value. We shall be referring to these numbers later on in power considerations and all. So alternating current and alternating voltage, we are trying to look at the same time, and I preferred omega equal to 1. So here you can see that the red line indicates the sinusoidal instantaneous value of voltage, which is fluctuating about time axis, and current is being shown by a blue line, wherein amplitude of the current I have shown little smaller than the voltage amplitude, just to distinguish. And here you can see that both the signals are in phase. I mean, current in the circuit or current delivered by the source is in phase with the voltage. This is a very usual normal condition that a voltage alternating sinusoidal voltage source is capable of delivering this kind of instantaneous voltage and instantaneous current. Now, here we can quickly go through an animation that how these currents are rolling. So on the given time scale, sinusoidal voltage and current is fluctuating in this fashion. So they are in phase. Both are at peak positions at the same time. Now we shall discuss AC in pure resistive circuit. V of t, that is instantaneous voltage, is equal to V0 sine omega t, and VR is the voltage across resistance, and by Ohm's law we can write V equal to IR. So as voltage is fluctuating as a function of time, applied voltage, so voltage across resistance will also fluctuate, and obviously the current will be function of time. What way it will be function of time, that we are trying to find out in this discussion. So voltage across resistance is obviously equal to the voltage that we have applied, and by Ohm's law on left hand side we can write I of t into R equal to V0 sine omega t, and here you can unfold I of t. So I of t is equal to V0 upon R sine omega t. So normally we prefer to write I of t equal to I0 sine omega t, where I0 is V0 upon R. Again a kind of Ohm's law for peak values. So we have completed this discussion very quickly, in a sense that V of t is equal to V0 sine omega t and I of t is equal to I0 sine omega t. So here it is again in the same fashion that value of resistance is something more than 1 ohms. So the current is less than the voltage levels because it is V0 upon R. So if we consider V0 equal to 1 volt and value of resistance something greater than 1, then I0 will be less than V0 on the scale, whereas we have time on x-axis. Now power in the circuit. Power P of t we can define as V of t into I of t. Normally in the electrical circuits, power we define current into voltage. So we have two sine wave signals of different amplitude but same omega. So the equation of power becomes P of t equal to I0 V0, V0 I0 into sine square omega t. So sine square function can be represented by this pink line. This pink line is indicating the power, and as this is a square function, we have power always positive. In the first half cycle, power delivered is positive, and in the negative half cycle, again the power delivered is positive. Now quickly we shall go through a beautiful animation of voltage, current and power. So here current and voltage are rolling as a function of time. Now the third green color line is representing power, and the power is fluctuating in the circuit. Here is flowing always above x-axis, time axis. So power delivered is positive. So here a pair of lines, a pair of circles are being described, and they are in phase. One corresponds to voltage and another corresponds to time. So here I just want to highlight a point that voltage describes one complete cycle, current describes one complete cycle, and power describes two cycles. So later on we are going to encounter with twice omega in the equations of power.